Jai Hind to all. My name is Dr. Divya Sharma, Assistant Professor in AKGEC Engineering College, Ghaziabad. Now, today's video lecture is on Digital Integrated Circuit Design. This topic is from Integrated Circuit. Its code is KEC 501. Now, first, CMOS logic circuit. First, we will cover CMOS an overview, then CMOS inverter and CMOS combinational logic circuits. Now, first, what do you mean by CMOS? CMOS, in this discussion, we will focus on the implementation of digital logic circuit using CMOS technology. CMOS technology is best suited for realization of digital systems, and reasons for this CMOS implementation means why we are using this CMOS technology by implementing this digital systems, means realizing digital systems. Reason is, first one is small size. Second is ease of fabrication, means fabrication is easy, low power operations, relatively simpler manufacturing process, and high impedance, allowing it to be used as a charge storage device, etc. So these are the reasons while we are using this CMOS technology. Now, CMOS overview. CMOS stands for complementary metal oxide semiconductor, and it is also known as complementary symmetry metal oxide semiconductor. Complementary and symmetry refers to the complementary and symmetrical pairs of N and P type MOSFET in its design. Now, main advantage of this CMOS is low static power consumption and noise immunity. In this CMOS, one transistor, CMOS is a combination of PMOS and NMOS. Now, here in this CMOS technology, one transistor of a pair is always off. The series combination draws significant power only momentarily during switching between on and off states. Now, this is the structure of CMOS. Here we have P substrate, N well, and here terminals are drain, main terminals are drain, gate, source. Now, first, CMOS. CMOS is a combination of P channel and N channel. It stands for metal oxide, is complementary metal oxide semiconductor. Now, and MOSFET, CMOS, MOS is MOSFET. So, MOSFET stands for metal oxide semiconductor transistor to implement logic gates. Now, study of CMOS inverter. In this section, we will study CMOS inverter, how to design CMOS inverter, and CMOS using AND or NAND NOR logic gates. Now, first we should understand that CMOS inverter. CMOS inverter is a combination of, this is PMOS, this is NMOS. PMOS, here this is the symbol of PMOS and this is the symbol of NMOS. Now, here CMOS inverter is a combination of PMOS and NMOS. Here you are giving input, this is your input, and here we will get output, and PMOS is, its terminal is connected to VDD, and NMOS one terminal is connected to VSS, or you can say ground. So in this inverter circuit, CMOS inverter circuit, two complementary MOSFET PMOS and NMOS are connected in the CMOS inverter. Input I serves as gate voltage for both the transistors. So this terminal is gate. Okay, so this serves as a gate voltage for both these transistor PMOS and NMOS. Now, NMOS transistor has input from ground and the PMOS transistor has input from VDD. The output terminal O serves as the output for both PMOS and NMOS. Now, when a high voltage VDD is given at input 1, when we are giving input 1 is logic 1, or you can say high input you are giving to this CMOS inverter. If it is 1, it will give you 0. How it will work, we will discuss in the next slide how we will prove that it is 1, and if we are giving input 1 and output is 0. When the high voltage VDD is given at the input, the NMOS is turned on, and while the PMOS is switched off, the output is pulled down to VSS or ground. Similarly, if we are giving low gate voltage, means we are giving input here 0, so we will get output here 1. Now, this is the structure of CMOS inverter. This is your PMOS and this is NMOS. Or you can say this part is pull up network, and this one is pull down network. Here we are giving input from here. This is your input part. This one is your output part. This is your PMOS. One terminal is connected to VDD and one terminal of NMOS is connected to VSS, or you can say ground. Now CMOS inverter. CMOS inverter means if we are giving input 1, then output should be 0. If input is 0, then output should be 1. So here this is the truth table of the CMOS inverter. Here we are giving 0 input, output is 1, and output is connected to VDD, means output is connected to VDD, so logic output is 1. Here input is 1, output it should be 0, and it is connected to ground. Now we will see working of the CMOS inverter. If input is 1, it means what? It means NMOS is on and PMOS is off. If input is 1, NMOS is on and PMOS is off. So if it is 1, this one is off. This one is off means it is open circuit. Here we are giving input from here. This is VDD and this one is ground. So if input is 1, so PMOS is open circuit and NMOS is shorted, means it is on, it is shorted and connected to ground. So here this is the output. So output is connected to ground. So output is equal to what? Output is equal to 0. Now if input is 0, then output should be 1. So if input is 0, it means NMOS is off and PMOS is on. Here is a bubble is connected here. So if you are giving here 0, so you will get here 1. Okay. So if it is 1, it means PMOS is on. Here PMOS is on. Now in this case, when you are giving input 0 and NMOS is off. Okay. Now if PMOS is on, it means this is VDD. PMOS is on. This is your PMOS. This is connected to output. From here, you are giving input. And NMOS is open circuit. It means this is open circuit and connected to ground. Okay. It means what? Output is not connected to ground. Output is connected to VDD if your PMOS is on and NMOS is off. So output is connected to VDD means VDD is 1. It means output is 1 when you are giving input 0. Okay. So this is the logic of CMOS inverter. When you are giving input 0, then output is 1. It means output is connected to VDD. When input is 1, output logic is 0 and output is connected to ground. So because of that, it is equal to 0. So this is the working of CMOS inverter. Now CMOS, we will study CMOS combination logic circuit. What are your basic gates? Actually basic gates are AND or NOT and universal gates are NAND and NOR. So these are combination logic circuits. So we will study the CMOS implementation of basic gates, universal gates. Like, okay, now study of CMOS logic circuit is essentially an extension of the CMOS inverter. Means first you should know CMOS inverter, then only you can proceed for the CMOS implementation of AND or NOT gate and universal gates. And universal gates are NAND and NOR. Now here already we was discussed that CMOS inverter. In the CMOS inverter, it is a combination of PMOS and NMOS. PMOS is pull-up network and NMOS is pull-down network. Now here also in this CMOS logic gate, it is also here in this case of CMOS logic gates, here is the same terminology that we have to use PMOS and NMOS, and PMOS is, you can say, pull-up network and NMOS is pull-down network. And here also if you are giving input 0, pull-down network will operate for input combinations that require a low output. When you are giving input 0, then your NMOS is off and PMOS is on. If you are giving input 1, it means when we are giving input 0, it means PMOS is on and NMOS is off. If you are giving input 1, then NMOS is on and PMOS is off. So this is the same procedure for when we are doing CMOS logic gate. Logic gate means if we are doing a CMOS implementation of logic gates. Now CMOS combination logic circuit AND. Now we will study here for the AND logic. AND is means what? Let it be Y is equal to A dot B. Dot stands for AND. Dot stands for AND. And if we are designing CMOS, here CMOS logic for this AND gate, it means we have to design it on the basis of NMOS. Now in NMOS, here this is the equation, logic equation for this AND gate. Y is equal to A dot B. For in the case of NMOS, A dot B, it is, if it is dot, it means A and B are connected in series. And in PMOS, vice versa of the NMOS. It means here in the PMOS, A and B are connected in parallel. Okay. So you should remember this logic. If here is a dot product means A and B are connected in series in the case of NMOS, and A and B are connected in parallel in the case of PMOS. So how we can design it? In the case of pull-up network, first we will cover pull-down network. So pull-down network is your NMOS. Okay. So pull-down network is NMOS. It means A and B are connected in series. So this one is A. This one is B. This is ground. This is pull-down network. Okay. So this is pull-down network. And in the case of pull-up network, A and B are connected in parallel. So A and B are connected in parallel. Okay. Now this is pull-down network and this one is pull-up network. So pull-up network is connected to pull-down network, right? And pull-up network, one terminal is connected to VDD, and pull-down network, one terminal of this pull-down network is connected to ground. These are your inputs A, B, B, and output you will get here. You will get here out. So this is the designing of CMOS implementation of AND gate. Now CMOS combination logic circuit OR gate. OR means Y is equal to A plus B. So here you have to implement CMOS implementation of this OR gate. Its logic equation is Y is equal to A plus B. It means A and B are connected in parallel in the case of NMOS. Here NMOS is pull down network. NMOS is pull down network, and A and B are connected in parallel. And in PMOS, this is pull up network. A and B are connected in series. So how we can implement it? CMOS means combination of PMOS and NMOS. Let us design a block diagram. This is your pull up network. This is pull down network. From here you are giving input by getting output from here. This is connected to VDD and this is connected to ground. So this is the CMOS implementation where you have pull up network means PMOS and MOS is pull down network. Input is giving from here. Output you are getting output from this terminal, and one terminal of pull-up network is connected to VDD and one terminal of pull-down network is connected to ground. So this is the CMOS implementation. Now here, how we can implement for OR gate? You can implement for OR gate PMOS. In the case of NMOS, A and B are connected in parallel. So A and B are connected in parallel, and A and B PMOS are connected in series. This is VDD. Okay. So this one is PMOS. This one is NMOS. So this is the CMOS implementation of OR gate. But you should remember, when you are giving input 0, your output should be 1. If you are giving here input is A plus B, here you are giving input A plus B. So you will get at the output terminal Y is equal to A plus B ka whole bar. Okay. So there are two options how you can implement CMOS technology. First is that you are giving input, means Y is equal to A plus B. It should be your output. And if you are giving input A plus B, your output, you are getting output A plus B ka whole bar. So you can connect CMOS here at the output terminal. CMOS means this is your PMOS, this is your NMOS, this is connected to VDD, here this is connected to ground. You will get output here. Now this is CMOS inverter. So in this CMOS inverter, PMOS is connected and NMOS is connected in pull down network. So here you are giving input A plus B, you will get A plus B ka whole bar at this output terminal. Now here, if you are connecting CMOS inverter here at this point where you are getting A plus B ka whole bar, you will get output here A plus B. Okay. And the another option is that, first option is this one, and another option is that Y is equal to A plus B. First you can convert Y is equal to A plus B ka whole bar, right? So A plus B ka whole bar means apply here De Morgan's theorem and A bar dot B bar. So here you can give inputs are A bar dot B bar and you will get output in this form A plus B ka whole bar. Okay. Now second is CMOS combinational logic circuit. This is the case of NAND. NAND is a universal gate. Now in this case, your Y is equal to A plus B ka whole bar. It means you are getting bar here. It means your input is A plus B. If you are giving input A plus B, then you will get the actual output A plus B ka whole bar. So here no need to give any, no need to change it, that you have to convert that A plus B ka whole bar. No need to change it. You are getting here bar. So Y is equal to A plus B ka whole bar. It means your input is A plus B. Your output is A plus B ka whole bar. So how you can implement in the case of NMOS, A and B, sorry, NAND is here A dot B. A dot B ka whole bar. So A and B are in series in the case of NMOS, and in the case of PMOS, A and B are in parallel. Okay. So in this case, when you are doing CMOS implementation, so NMOS, in the case of NMOS means pull down network, A and B are connected in series, and in PMOS, A and B are connected in parallel. So here A and B are connected in series. This is A, B, this is connected to ground. Here you will get the output. Now A and B are connected in parallel. In the case of PMOS, now in this case, your input is considered as A dot B. Means here A dot B is your input and you are getting output in the form of A dot B ka whole bar. It means you are getting Y is equal to A dot B ka whole bar while doing this CMOS implementation. So this is the CMOS implementation of NAND gate. So likewise we can do the CMOS implementation of NOR gate. Now here in the case of NOR gate, Y is equal to A plus B ka whole bar. It means in the case of NMOS, A and B are in parallel, and in the case of PMOS, A and B are in series. Okay. Now we have to do CMOS implementation of this NOR gate. Now A and B are in parallel in the case of NMOS. So A and B So this is the CMOS implementation of NOR gate, where this is the NMOS. So in the case of NMOS means pull down network, this is pull down network and this is pull up network. So in the case of pull down network, A and B are connected in parallel, and in the case of pull up network, A and B are connected in series. And terminal of this PMOS is connected to VDD and terminal of this NMOS is connected to ground. And here we are getting the output. If you are giving inputs A plus B, this is your input. So you will get output A plus B ka whole bar. So this is the CMOS implementation of this NOR gate. Let us consider an example. Y is equal to A dot in bracket B plus C dot D bracket close. So this is, let us consider this is an equation, logic equation. So you have to realize it using CMOS implementation. So how you can do it? C dot D, Y is equal to, and this is the whole bar. So Y is equal to A, B plus C, D, this one ka whole bar. This is the logic equation. Now we have to implement it using CMOS. So CMOS implementation, how we can do? C dot D. It means C dot D are in series in the case of NMOS. And then C and D are in series. Then B is in parallel with this C and D. So B is in parallel with the C and D. When C and D are connected in series, B is in parallel with that. And A is in series with this circuit. Okay. Now, can we implement it? First, we can, this is the case for NMOS. So, you should remember the case for NMOS, and in PMOS, we can take the invert property. Means if C and D are in series in the case of NMOS, then C and D are in parallel in the case of PMOS. So, how you can implement it? C and D are in series. This is C, this is D, are in series. B is in parallel. So, this one is in parallel. Now, C and D are in series. B is in parallel with C and D. Now, A is in series with this whole circuit. So, A is in series with this whole circuit. So, this is your pull down network. Now, here we can connect output. So, this is pull down network. Now, designing for pull up network. So, C and D are in parallel. C and D are in parallel. B is in series. series with this circuit. Now A is in series with this circuit. So it means A is in parallel with this circuit. Now whole this circuit is connected to VDD. Now here input is A dot B plus C D. This is the input, and output is equal to what? Output you are getting directly, that is equal to what? A dot B plus C D ka whole bar. So this is the CMOS implementation of equation y is equal to A in bracket B plus C dot D bracket close. So this is the equation, and this is the CMOS implementation of this logic equation. Now in the previous equation there is a bar, but here is a bar is absent. It means what? You have to take input A dot B plus C D ka whole bar. It means if you are taking input this one you are taking input, you will get output directly. Y is equal to A in bracket B plus C D. So can you solve it? Here this is whole bar. It means apply here De Morgan's theorem. A bar plus B plus C D ka whole bar. Again this is A bar plus B plus C D ka whole bar. It means B bar dot C D ka whole bar. How we can apply De Morgan's theorem? You all know De Morgan's theorem is equal to what? A plus B ka whole bar is equal to A bar dot B bar. It means if here is addition sign and whole bar is here, so addition sign is converted into dot product and whole bar is separated, divided, A bar dot B bar. And if A dot B ka whole bar, so that is equal to A bar plus B bar. So this is De Morgan's theorem. Now apply here De Morgan's theorem. Apply here bar, whole bar, A dot B plus C D ka whole bar. So if we apply here De Morgan's theorem, it means A bar plus B plus C D ka whole bar. Now here A bar plus, here is the whole bar. So apply here De Morgan's theorem. That is equal to what? B bar dot C D ka whole bar. Now again you will get equation A bar plus B bar dot C D ka whole bar. It means C bar plus D bar. So this is the actual equation when we are solving this bar. So this is your input. If this is your input, you will get output in this form. Okay. So consider here this is the input. So here C bar and plus D bar means plus is here. It means C bar and D bar are connected in parallel. So here we can implement it. C bar and D bar are connected in parallel. And B bar is connected in series with this circuit C bar and D plus D bar. So B bar is connected in series. And A bar plus, it means A bar is parallel in this circuit. So A bar is parallel with this circuit. So this is your pull down network. Pull down network, or you can say NMOS network. Now we have to draw the PMOS. PMOS for this, here C bar and D bar are in parallel. So C bar and D bar are in series. C bar and D bar are in series, and B bar is connected in series here in the case of NMOS. So B bar is in parallel with this circuit. Okay. Now here A bar, this is A bar. A bar is connected in parallel with this circuit. It means A bar is connected in series with this circuit. And this is connected to VDD. This is connected to ground. We are connected. These are your inputs: A bar, B bar, C bar, D bar. And from here we will get the output. This is the output. So input is here. Input is A bar plus B bar in bracket C bar plus D bar. And output is equal to what? Output is equal to Y is equal to A dot B plus C D. So this is the output of this. This is the output logic equation. So this is the CMOS implementation of Y is equal to A dot B plus C D. Next, let us consider this is also an example. Y is equal to A B bar plus A bar B. So we will do it by using this second logic, that A here is Y is equal to A B bar plus A bar B. It means A into B bar, if you are taking NMOS, the case of NMOS. So A and B bar are connected in series. And these one also are connected in series. Now both are connected in parallel. Now we can implement for the case of NMOS. So A and B bar are connected in series. Sorry, A and B bar. This is A. This is B bar. A and B bar are connected in series. A bar and B. So here A bar and B are connected in series and both are in parallel. It is connected to ground. So this is your NMOS. Now for the PMOS, A and B bar are in series. Here is in series. So A and B bar are connected in parallel. And again A bar and B bar are also connected in parallel and in series with this circuit. This one is A bar and B. This is connected to VDD. Here this is the output. Now here input is A B bar plus A bar B. So output is what? Output is equal to A B bar plus A bar B ka whole bar. Right? Input is here this one and output is equal to this, means whole bar. So can you convert it in the form of A dot B bar plus A bar dot B? So output is connected to CMOS inverter. So this one you can connect it with, this is PMOS. Here this is connected to VDD. So here A B bar plus A bar B ka whole bar, and here you will get output in this form A B bar plus A bar B. Okay, it means what? It means if you are taking input A B bar plus A bar B ka whole bar, then you will get this output original this logic circuit. So this is the CMOS implementation of this example, Y is equal to A B bar plus A bar B. So these are the references of the CMOS implementation. There is a design of analog CMOS integrated circuit. This is TMH publication, and Salivahan electronic devices and circuit. This is also TMH publication. So these are the references of this topic which is covered. Thank you.